Turing recognizable. They're pretty well synonymous. Alright, so what is an enumerator? And exercise 3.4, at the end of the chapter, it asks for a formal definition of an enumerator. Now, as given in the text, personally I felt it was a bit fuzzy, not particularly clear. That didn't go into details too much, but some there's some details there. So let's say, talking about the relationship between the standard Turing machine, let's say just machine M, and an enumerator, that's the printer added version of the Turing machine. Well, now these are some of the details given in the text. Personally, I didn't find it terribly clear, as I just mentioned. So it'll start with a blank tape, and if the enumerator doesn't halt, it's just typing out accepted strings, and it doesn't halt. So if it's not a decider type Turing machine, it may print out an infinite, an infinite, that's the infinity sign, an infinite number of strings, and you can talk about a language that is enumerated. What does that mean? Well, it's analogous to earlier definitions of languages. Language recognized, language, in this case, enumerated. That just means it's the set, the set of all strings that are printed on the printer by the enumerator. So in other words, it's the set of all strings enumerated, right? So one after the other. Now, here's what I found a bit unclear. So this, call the enumerator, the variant of the Turing machine, call it E, label it E. So it can generate these strings, prints them up on the printer, in any order, and perhaps with repetitions. Now, why that's the case, I didn't find clear. Not sufficient details. And my impression is Turing probably just added this when he's going through text and looking through, were any gaps, have I missed out anything? And my impression is he just sort of added this, popped this in, and without going into full details. That's my impression when he is writing the text. Anyway, so here's a theorem. Makes a connection. Once again, it's an if and only if type. Makes a connection between Turing recognizable language, just a conventional Turing machine, call it M. It accepts those strings of the language, and so a language is Turing recognizable, if and only if there's some enumerator that enumerates it. So effectively, that means for every string, well, it's both ways, of course, if and only if, but effectively it's saying if a string is accepted by the machine, the Turing machine, standard Turing machine M, then it'll be printed out by the enumerator, by the printer. Okay? Now, and it'll go both ways. Okay. All right. So once again, I've done it in pure math style. So the if part first. So this statement, again, I've written out the two mathematical statements of a if and only if type proof, label them P and Q. So typically, such a statement is of the form P IFFQ, P if and only if Q. And convention is in pure math start with the if part. Okay, so in other words, P if Q. So P is true if Q is true, and if you rewrite that in if then type format, it comes out as Q arrow P. In other words, if Q is true, then P is true. P is true if Q is true. It's just saying the same in reverse order effectively. So if Q then P. So the if part means you assume is the right hand side, the Q is true, and you try to prove in the theorem, you prove that the left hand side, P, is true. Alright, how to do that? Here's the proof. Okay, so so we start with Q. Okay, so that is, so we're going to show that if there's an enumerator, called E, that enumerates a language. So we call the language A. So in other words, it's just printing out all the strings of that language. Okay, now that's a pretty strong clue. All right. So if it's doing that, that's what the enumerator is doing. It's printing out each accepted string of language A. Yeah. Then there is, there is sign in pure math here. Then there is a Turing machine M that recognizes A. In other words, accepts all the languages, so all the strings of language A. Okay. So how does that work? Well, let's see. So you input a string, okay, to your Turing machine M, and you run E. You get your enumerator, that version of the Turing machine with the printer. You get it running. So every time E outputs a string, compare it with W. Okay? This is the string that's input to your machine M. And if ever, this string W, if ever it's output by the enumerator, so now you can see this, probably see this top line the next session. Except, just have your Turing machine M except whenever your E, your enumerator, outputs a string that's the same as your input string for your machine M. Okay? In other words, W, that string W. Right? So in other words, whenever the E is printing a string W, Turing machine M is accepting it. Right? So doing the same job, equivalent. Okay? So therefore, clearly M accepts those strings that appear on E's list, on the printed list. Okay, so that you've proved, so that in other words that's P. That's, so therefore, the language is Turing recognizable. That means every string in that language is accepted by a Turing machine M. Okay. Well, that's P. That's the statement of P. The language is Turing recognizable. So we proved the half of it, the if part, and the only if part we'll do next session.